Good morning, everybody. I'm Michael Osman of Gray Scott Gadgets. I want to talk to you this morning about a little project that's been kind of a fun side project for me for quite a few months now, and I had it in mind to submit to GNU Radio Con this year for a long time, and then we became sponsors of GNU Radio Con, Gray Scott Gadgets, and we get a time slot for free, so I didn't even have to go through the CFP. But that means you get to see something that isn't peer-reviewed, so win. So I'm actually this is kind of a work in progress, and I want to show you what I've come up with and the problem that I'm trying to solve. And I'm really interested in feedback from this group. I'm going to show you a couple of things that I'm probably doing wrong, and I'd love for you to tell me what I'm doing wrong later. But I'm also going to show you some things that maybe you hadn't thought about before. So before we get rolling, I do want to mention, we are a sponsor. You can visit us over in the booth over there. And, I forgot to I guess I put the slide up in the back instead of the front. But I'm going to give you a reminder at the end that we have an open house on Friday, and we'd love to see you there. This is the state-of-the-art in reverse engineering of digital radio systems in the information security community. I got this screenshot. I pulled it off of Sammy Kamkar's website, and hopefully some of you have seen Sammy and his videos online. Wonderful, creative hacker who's done a lot of interesting security research, and he's learned to use GNU Radio and SDR and some other wireless tools over the last couple of years, and he's doing things where he often, and I'm not really trying to pick on Sammy. Sammy's wonderful, and he's doing terrific work. I'm using him as an example because this is very exemplary of what goes on in the information security community among people who are reverse engineering wireless communication systems. What he does is, his workflow, at least for this project, was that he used software-defined radio, including GNU Radio, to find a signal, identify it, filter it, demodulate it, and then he got stuck. And he turned to tools outside of GNU Radio to deal with pulling bits out of this demodulated waveform. And this is extremely common. And here's another one. I mean, we laugh because it's true, right? I mean, I know that there are plenty of people in this room who've done something like this, right? I mean, don't lie to yourself. You know you've done this, right? So this is a screenshot from Mike Walters, and he's a developer who's doing a lot of exciting stuff with software-defined radio lately. Actually, we have a demo over at our booth with just some code that he primarily wrote going on right now. And he is the primary developer of InSpectrum, which is a signal analysis tool that I've been talking about for a while. It's still very much in development, but it's an extremely valuable tool. And it was when he did this and he said, this is ridiculous. And the next day, he started adding tools inside InSpectrum to avoid having to do this. And anyway, I wanted to give you a little demo. Yeah. And I thought, well, I need just a quick and easy, simple digital wireless system to kind of demonstrate with. And I was in the bookstore yesterday downstairs, and I saw these iClickers on display. These are these instant audience feedback devices that what are like all the undergraduates required to buy these? Open source. These things are they have a unique ID, and they let you push a button, and they let you poll the audience and get instant audience feedback. They also let you, take a quiz or take attendance. So I noticed that these are iClicker Pluses. So of course I had to buy one. I did not buy the iClicker skin for $9.99. But this is an iClicker Plus, and the first time I ever saw, this is the first time I've seen an iClicker Plus, but I saw an iClicker, the first generation, for the first time several years ago. I was working down the road at the Boulder Labs, and I had an intern who was a student here at the university, and come August or September, he rolled into the labs and he says, "Hey Mike, guess what they made us buy at school?" We had one of these. He was like, "They're taking attendance in lecture halls with these things." And he's like, "Can we reverse engineer it?" And I don't know why he wanted to reverse engineer it, but we did. And he has some code. He put up some code, GR Clicker. If you look for that, it's probably not up to date with recent GNU Radio, but it's some example code you can look at and see how things work. But I decided I should buy an iClicker Plus and just do some basic packet captures and see if it looks like the iClicker did several years ago. So I'm going to just kind of give you a little live demo here, except I'm not going to bother capturing it. I'm just going to use a capture that I took yesterday. But if I go, and I'll start out by using InSpectrum. I have this file. I'm going to remove, oops, that's not the right command. I'm going to remove some of these temporary files here. But I have these iClicker capture files that I took yesterday that if I fire up InSpectrum on one of them, you can see what InSpectrum looks like. It's a spectrogram with time going on the horizontal axis and frequency going on the vertical axis. And if I scroll through here, this is captured in the 900 megahertz band. Look at these really prominent events. They're pretty brief. These are at 917 megahertz, which is one of the channels. I think it's the initial channel that this thing uses until you tell it to use a different channel. And if I zoom in here, and I need to use the power of open source and actually contribute a better zoom centering feature. But if I zoom in here, you can kind of see, maybe that looks a little like FSK. If I reduce the FFT size, you can kind of start to see the distinction between those frequencies a little bit more. Sometimes you can do that, sometimes you can't, and like actually read the FSK modulation in a spectrogram. It depends on how fast the modulation is versus your FFT bin size and your sample rate. But InSpectrum has this cool thing now where you can right-click and say Add Derived Plot, Frequency Plot, and like move this over that section and adjust its filter. And look at this. Now I've got how the frequency changes over time right down here. And then I can enable cursors, which is cool. I can do something like, let's say I want to enable, I'm cheating a little bit because I've already counted the symbols here. So I'm going to go slightly more than the number of symbols that are in this packet and enable a cursor that has 92 segments. And I can kind of line it up down here with this, the beginning, or this first zero crossing that I see right there. And I'm going to get rid of this little panel here so I have more screen real estate. And pull this over, and you can see, like right around here, I can just kind of use this cursor to line things up. I'm not paying attention to the spectrogram up above. I'm paying attention to this frequency over time plot down here and trying to line up my vertical dashed lines with these zero crossings. And now, InSpectrum tells me my symbol rate, 152.5 kilohertz, or 152.5 kilosymbols per second, which is almost exactly what we observed with the original iClickers a few years ago. Aha! And it tells me the entire period of this whole area that I've covered with this multi-part cursor is about 600 microseconds, which is also similar to what we observed some years ago. And I can also make another derived plot from this one. I can add a threshold plot, which then thresholds it into zeros and ones. And then I can right-click and say extract symbols. And if I go to my terminal here, there are my bits. Okay? This is what you should be doing, not using a piece of paper. If you need to do a one-off decode like this, it's super fast and easy. Anyone can learn to do it, in 5 minutes. And here you go. You can really easily see 10, 10, 10. That's that preamble of alternating bits at the beginning of the packet. And I could take this and I could paste it into Python shell or C source code or whatever and hack around with it and start comparing packets against each other. But here's the next problem that everyone runs into is in reverse engineering a system, they like to capture a whole lot of packets and start comparing them against each other. So what do we do there? InSpectrum doesn't really help us so much with that. Right? This is a terrific tool for a one-off. Finding the signal, figuring out some basic properties, extracting one packet, sure, terrific. But what happens if you want to do 100 packets? So what I'm going to show you now is a little GNU Radio Companion flow graph, because GNU Radio Companion is what I use all the time for this kind of stuff. And I have a iClicker something or other flow graph. There we go. Okay, so I'm taking a file source, which is the same capture, And I'm running it through a frequency translating filter just to shift it to shift my center frequency and filter out the stuff I don't want. Then I have this little section here, and I'd love it if somebody tells me that there's a better way with fewer blocks to do this, but all I'm doing is burst detection. I'm just setting up something so I can run my signal through a burst tagger, which then gives me a tag at the beginning of a burst of energy and an end tag at the end of the burst of energy. So I kind of tag every individual packets. I'm using stream tags, which I heard people talking about as I was walking in the room. And then I run it through quadrature demod, and this is disabled here. So I'm just going to run it through quadrature demod and into a Qt GUI time sync. I'm going to set this repeat to yes so that we can kind of see the same packets over and over again. And now the Qt GUI time sync is triggering on this start of burst tag. And this is the end of burst tag here. So you're seeing the same thing that I saw in Spectrum from the derived plot. This is being produced by that quadrature demod block, and then it's getting tagged so that these are very brief, transient packets. If I didn't have this tagging, I would be very lucky to once in a while catch a glimpse of a packet. But because I'm using this burst tagging, I'm seeing my time domain plot here triggering and only showing me packets that have triggered that burst detection. And so then what I like to do, once I have that kind of working and I've verified that visually, I go in here and I set my file source to repeat no, and I add in a tagged file sync. This is a pretty useful way to go. And then I run this flow graph, and it's going to do the same thing and go through however many packets are in this file. It's not that many, half a dozen or so. It's done. And if I close that, now I have these files, these .dat files that were created. And each one is the demodulated waveform of one of those bursts. So it's a list of floats. And look, they're only about 9,400 bytes long. And if you interpret them as floats, you can kind of see, they're sensical floating point numbers. And if we were to plot one of these, it would just look like exactly that plot that we saw in Spectrum, the frequency plot, or the plot we just saw in the Qt GUI. And now I'm going to show you kind of a concept that I've been working on. I'm going to look at my slides a little bit. No, I didn't put in slides for this. The concept here is, if you think about what we saw in Spectrum, you remember how easy it was? Even before I put the cursor across it, you could kind of eyeball it and read a lot of the symbols, right? The only thing I really need the cursor for is to differentiate, like when there's a long string of zeros, like was that 8 zeros or 9 zeros? But for the most part, you can eyeball a packet and just read the bits off the screen, right? Once you get to that waveform that's just like one dimension varying over time, your eyeball is really good at that. But what happens is that what happens with folks like Sammy who try to use tools like GNU Radio, they get this far. They figure out capturing a packet, they figure out filtering it, they figure out demodulating it, and then they go and look for things like this or this. And these things are big and scary and complicated and hard to use correctly and don't work particularly well even when they are used correctly. And here's the key insight that led me to work on what I'm about to show you. The key insight is that these blocks have very little state. Mueller and Mueller clock recovery, for example, looks at one sample at a time. And it keeps track of an estimate of the clock frequency and an estimate of the clock phase. That's the symbol clock frequency and the symbol clock phase. And it looks at one sample. It has like 3 pieces of state. When you're looking at a waveform with your eyeball and you're seeing the entire packet plotted on screen, you have way more than 3 pieces of state. You have the state of the entire waveform at your disposal, and you can read it and know what the bits are. These algorithms use a very much smaller amount of state, and they have trouble sometimes doing what your eye can do. And in software-defined radio, often, and especially when we're doing reverse engineering, we are frequently in the scenario where we have an entire waveform, an entire packet waveform in memory. So why don't we use all that state? Sometimes we want something that's lower latency, that can start synchronizing right at the start of the packet so we can do real-time processing. But a lot of the times we don't need real-time processing. So let's use the state that we have available and do something a little bit more intelligent. So I'm going to show you a little Python tool that I wrote, and I'm just going to walk you through it actually in IPython. I will run this Python program here, which gives me this waveform in a variable called samples. That's just one of those files, those file.dat things, just loaded into a Python tuple. And then I'm going to threshold it based on the midpoint there. So I'm going to just make a little array called b, and it's going to be samples greater than midpoint. I don't have time to get into my midpoint function, but it is worthy of some discussion at some point. And then I'm going to take the differential of that. So I'm going to subtract like one sample from the next, or one sample from a subsequent previous sample, or something like that. I'm going to use numpy.diff of b, so every single sample gets subtracted from the next. And then I'm going to square that, so that when there's a transition up, I get a 1. And when there's a transition down, I get a 1. And when there's no transition, I get a 0. And this is what you might call pulse conditioning. This is very common to do something like this in a clock recovery scheme. And if I plot samples and I plot D, then you can see my original waveform is the blue curve, right? That's the frequency demodulated waveform. And my pulse conditioned waveform is the green one. And all it is a train of pulses. Every time there is a zero crossing, basically, in my original waveform, I get a pulse. So every time there's the start of a symbol, I get a pulse. And then what I do is I use the power of the FFT to analyze that pulse train. And so what I'm going to do here is I'll say F equals FFT of D, and I'm going to make it the length of samples. And now if I plot F, this is, how about I try plotting the absolute value of F, the magnitude, because F is full of complex numbers, but I just want their magnitude. If I show that, that's a little bit, let me try that again, there. If I show that, now this is the frequency domain representation of that train of pulses that I created out of my original waveform. And this really prominent one here is that frequency bin is my clock frequency. I can just use the FFT and pull this out. Now, it isn't necessary. I've tried various approaches of selecting which bin, and that's worthy of discussion I don't have time for, but it's not always the number one highest bin that you see, but it often is. But in this case, it's pretty obvious to me because it's the highest. It's a high bin that has prominent harmonics. Sometimes you might see harmonics that actually end up higher than the fundamental or whatever, and you need to kind of look for the fundamental. And this particular bin is bin number 90. You can kind of see at the bottom of the screen there. And if I go, I just accidentally nuked my terminal. If I go look at that particular bin, I'm going to have to catch up a little bit here. Sorry about that. Run. So this is a good review of what I have to do here. Perfect. Perfect. So I have this waveform, right? It's just a one dimension varying over time. And then I'm going to take the midpoint and threshold over that midpoint greater than, all right? And then I'm going to take the differential of that result and square it. You could take an absolute value here instead of squaring it, but I've been squaring it. And then I'm going to take the FFT of that conditioned pulse train. And then we plotted that and saw that bin number 90 was the most prominent one. I have this, and if we look at bin number 90, we see it's a complex number. It has a magnitude. We can verify this. I mean, we saw this in the plot, but we can verify that its magnitude is high relative to its neighbors. Okay, that's good to know. And here's a really cool thing. The angle of this complex number. That's the clock phase. I had to find the clock frequency and the clock phase, and the FFT gave me both. Isn't that awesome? Now all I have to do is take my knowledge of the clock phase and my knowledge of the clock frequency and walk through and select the samples that line up with my symbol clock, dump them out. And so what I do is I do this find clock frequency, and I give it the power or the magnitude spectrum, just like I did visually. This is a little algorithm that maybe requires further study or discussion or improvement, but it tells me that bin number 90 is the one I want. And then I kind of put it all together with this thing, whole packet clock recovery, that does all those steps for me. And that is not quite what I expected. Oh, there. Okay. If I had debug on, so it's giving me a bunch of output here. It tells me 90 was the bin I wanted. It tells me that means I had 26.2 samples per symbol, right? So that's how many samples it has to walk through. It's not doing interpolation, but it could be. It's just picking every sample that is nearest to that 26.23. It checks the clock phase, and then it dumps out the samples that occur at that value. And then I can slice it, so like the ones that are positive become a 1, and the ones that are negative become a 0. And I have this all actually in a tool. I mean, you can run it from IPython, or you can just grab a random one of these DAT files and point this Python program at it. And look at that. That was a different packet that I just gave this. Now let me grab another one. That was a different packet. Every time it's selecting bin 90 because I have very consistent symbol rate from packet to packet. And you may notice that I have very consistent packet data from packet to packet. And at this point, we can analyze that super easy in Python, or you can copy and paste these. I can just do like for file in file star do something like this, and just have it dump out all my packets for me, right? So like, it's not particularly speedy, right? I haven't done anything to optimize this, but it requires 0 configuration. All I have to do is give it the waveform that I'm interested in doing clock recovery on and pulling bits out of, and it figures out the clock frequency with 0 configuration and figures out the clock phase and dumps bits out for me. And this, I think, is the kind of tool that reverse engineers need to be able to avoid doing stuff like this. These kind of techniques, and especially now that we can automate them with things like InSpectrum, are still useful for one-off needs, right? But when you need to do hundreds of packets or thousands of packets, I think it's valuable to have in our toolbox a type of technique of clock recovery that takes advantage of the high memory systems that we have available to us. You know, the clock recovery, like Mueller and Mueller clock recovery, that algorithm was invented in the 70s, right? It was not invented for high memory systems. And the only real advantage of using those older clock recovery, more traditional clock recovery algorithms, I think, the only advantage in an SDR world is latency and performance, right? If you're trying to make a high-performing, low-latency, real-time system, then yeah, you're going to have to spend some time finding the right clock recovery approach. But if you don't have those needs, why go through the pain of using Mueller and Mueller or any of the other traditional clock recovery algorithms when you can use when you can take advantage of your high memory and do something like what I'm doing. Now what I'm doing is just one implementation. It's on GitHub. My GitHub account is Mossman under clock recovery. Look for that wcr.py. You can take a look yourself. I already showed you the essential elements of it. There are a lot of variations that could be made on it, like how do you select the bin out of the FFT? That's definitely up for debate. And there are certainly other techniques that I haven't thought of, I'm sure, that could be used that take advantage of high memory availability to do clock recovery. And so this is just kind of a first effort, something I threw together that I've found useful already. And I haven't done any quantitative testing on it. I think there's a lot of further work that could be done to make it better and more user-friendly. I haven't put it into GNU Radio, for example. I just have this kind of hacked together Python script. But hopefully you get the idea that there's some value here, I hope. And before we wrap up, I do want to say we are having an open house on Friday, so just in case you didn't know, at our labs in Evergreen, which is about a 45-minute drive from here. If you are interested in coming but don't have a way to get there, we have put some sign-up papers at our booth to like share a ride, need a ride, have a ride to share. So if you have a ride to share or need a ride, swing by the booth and put your name down, and hopefully we can get you in touch with somebody who you can share a ride with. We don't have much time though, so do that today, and then hopefully we can have you coordinated with somebody tomorrow. So if you are interested in coming and need a ride, please do that. And we'd love to see you there and see you around the conference. And do we have a minute for a question or two? All right.
All right. Do we have any questions for Mike? See Tom raise his hand.
Recovery. So I think this is good work. I do want to there's a couple things. First, to keep the point that this is from a reverse engineering standpoint, whereas me and I think a lot of other people, we do need a real-time streaming. That's what we're trying to do, is build that. So I just want to make sure that that is a distinction really worth making. The other thing is just to defend the polyphase filter bank clock recovery algorithm. Because you're absolutely right that the Mueller was designed decades ago under conditions, actually was designed under hardware-based conditions. And this is one of those things that I talked about on Monday, and people have heard this from me forever, that we learned from software radio. We started with our hardware-based techniques that we were limited by that. We transitioned to software radio. We took our hardware-based techniques and we coded them up. So that's essentially how the Mueller gets into software radio. That is a much more modern concept of doing clock recovery, thinking about it more from the original mathematics of how you want to do clock recovery. And again, in its defense, I've actually tracked signals down to 0 dB SNR with that block.
Nice.
So when you get it to work, and I will admit parameterizing that thing is hard, mostly that TAPS line there. For for a while, I think I was the only one in the world that could figure out what those TAPS were.
I think so.
I have there are tutorials out there that actually explain that better, and people have started to use this properly. But when it's used properly, it actually does work very, very well.
Yeah, thanks, Tom. And I totally agree. Like, if you're using Mueller, I strongly encourage you to use switch to polyphase immediately. But it does have a learning curve, and for folks who are oftentimes learning DSP for the first time, especially folks in the security community who are learning DSP, and they see this and they're like, what's a filter? Why is there loop bandwidth? Where's a loop? And like, they have no idea what a lot of this stuff means, and what are all these extra outputs, and do I need them? And it's not particularly user-friendly, but it is particularly effective. However, for some cases, I would guess, I haven't measured this, but I would guess that there are cases where this is going to fail, where my whole packet technique may succeed. And in particular, the kinds of cases where you may see a discrepancy there are things like packet formats that don't have preambles. I see this a lot with on-off keying. On-off keying, if you just amplitude demodulate it and throw it into whole packet clock recovery, you get a bunch of ones and zeros. And oftentimes, those are just pulses and anti-pulses that don't have any kind of a preamble that is designed for a clock recovery system to catch up with. So there are going to be like the most general case, like any kind of digital packet with a consistent symbol clock, that's what I'm trying to be able to support with what I'm doing.
Okay, I think we have, oh, louder than I thought. I think we have time for one more question, and if Doug could come up and start getting set up for the next talk, that would be great. Any other questions? No? All right, well, let's thank Mike.
Thank you.
Thank you. So I do once again want to highlight that Great Scott Gadgets is a platinum sponsor of the conference. They have a great booth set up in the vendor room, so be sure to go check them out.